to our PolarConnect event. We're really excited to be actually talking with a team that is in remote parts of Antarctica. We'll let them describe what they're doing, but we call them the Ice Shelf Flow and Fracture Dynamics Research Team. They're part of PolarTREC, which I'll get into in a moment. Today is October 19th, 2016 in North America. It's a day ahead down there in Antarctica. And we're really excited to see so many people joining us from all over the world. Before I turn this presentation over to the research team, there's a few things that we're going to go through. One of them is we will not be using a webcam for the rest of this presentation. And the team does not have access to a webcam either, so that's part of the reason for not having one. They do not have computer access, so even though if you say hellos and all those kind of good things and want to talk to the research team, they can't see your chat, so we'll try to be good hosts and relay the chat to them as we go along and your questions. Like I said, before I turn this over to the team, there's a few things that we want to share with you about PolarConnect events and how they operate. As you can see, there's lots of people joining us. Some have joined by voice over IP, some have joined by phone. In either case, if you are not the presenters or the host of this webinar, we really would like you to mute your microphones until it's time for questions. You can click on the little microphone at the top of your application window, and you should get a little X through it or a slash to mute yourself. If you're joined by phone, you can use your regular mute button on a phone or *6 to mute and *6 to unmute. That will help a lot with the presentation as we go along. The team is calling in by satellite phones, and it's a great time to learn about satellite communications. But you will find that although we have a great connection with them today, it could drop at any moment as the satellite orbits the Earth, and we might lose connection or have a dropped signal for a little bit, and we'll have to wait until David or Lynn or Gordon rejoin us. So they may just drop off, and we'll let you know if that happens, and we'll just kind of wait to have them log back on. As we go through the presentation, I see that Judy, who is helping me, she and I work at ARCIS, is getting people to introduce themselves and tell us how many kids are in their classroom or other people that have joined us. Again, we'll share all this with the research team, but I would like them to know that there's at least 22 or so people that have signed on. All of them are mostly classrooms, so 22 plus however many students they're in, and they really are coming from all over, at least the United States at this point. Why is David in Antarctica and having the time of his life down there? It's because he's part of this program called PolarTREC, Teachers and Researchers Exploring and Collaborating. And what's exciting about our program is that we're funded by the National Science Foundation to place teachers like David from around the United States with researchers like Lynn and Gordon in Antarctica and in Arctic regions. And hopefully they learn something about what the science is going on down there, some of the issues that are happening in the polar regions, and they bring that back to their classroom and share it with all the kids that they work with over their career as well as other people. So we're really excited about our program, and it's administered by a nonprofit that Judy and I work for called the Arctic Research Consortium of the United States. And just to give you a point of reference, we have an office in Fairbanks, Alaska. That's where I'm calling from, actually, Anchorage, Alaska. And we have an office in Washington, D.C. as well. Questions. Everybody's going to have questions as we go along today. So because of our satellite connection, we'd like you to type them in the chat box, and I will interrupt David and Lynn and Gordon as we go along with relevant questions. And hopefully at the end we'll have time for you to actually ask your questions live. And, you know, we'll try to do it that way. So I'll remind you how to do it at the end. But in the meantime, just type them in the chat box. All right. So with that, somehow your opening slide is up, David, and it's called Robots in the Danger Zone. And I somehow right away that music, Danger Zone, came into my head. Yeah. Anyway, that's in my head. And we should have a soundtrack to this presentation already, I can tell. So I'm going to turn it over to you. And please cue us with the next slide. And I will also explain when we don't have animations to the rest of the group and how to find them as we go along.
All right. Well, good morning. And I'm here with Lynn Togzewski.
Hi.
And also with Gordon Hamilton, who is the principal investigator for the project. Hello up there. And so we're going to be going over what we're actually doing here. It's actually an amazingly beautiful day here in Antarctica. The sun is up now. It's 7 a.m. here in Antarctica, and it's tomorrow. So,
yeah, David? David?
So let's go ahead and move forward.
Hang
on 1 second.
Yeah, so I don't know if we lost connection on your phone, but we did, we can hear you through, we can hear you through another.
Okay, now I'm back over here. I just handed it off. Gordon's going to call in on the other phone. Okay, so, yeah, I just, my phone just stopped.
Excellent.
So where did I leave off?
You just introduced the team members, so just start from right now, from wherever you are right now.
Oh, in Antarctica. 7 a.m. The sun is coming up. Going really. Oh, did I just drop that one too? No.
Yes.
It was windy yesterday. All right, so let's go on to the next slide.
Okay.
So this
we're on
shows.
The Ross Ice Shelf.
This shows the Ross Ice Shelf, the leading edge of it. We are not anywhere close to that leading edge of the Ross Ice Shelf, but we're going to talk a little bit more about that. The Ross Ice Shelf is floating on water. So even though we're on ice, if we were to drill all the way down through the ice shelf, we would eventually see the ocean before we would actually see solid land. And our studies all relate to this particular area of the Ross Ice Shelf. All right, so the next slide. Ice shelves are feeded in through a whole bunch of different glaciers. The image over on the left-hand side shows approximately where we are. We are actually down near the bottom of that image where you kind of see this long black line coming down. We're down there. And you can see over on the right-hand side large black images. Those are other feeder glaciers coming into the larger Ross ice sheet. The reason for the images off on the right-hand side, when we talk about global warming and the contribution of the ice shelves to it, if you were to take a cup of water and fill it up with ice, so that the ice was floating on top, you were to think about, okay, well, what would actually happen if that ice was to actually melt? Would the glass of water overflow, or would it not? And in reality, if you actually sat there and you watched the whole thing, all the ice would melt in that glass of water, and nothing would happen. It wouldn't overflow. So the ice shelf itself, if the whole ice shelf disappeared and melted into the water, global sea level would not go up because it already is accounted for. What ice shelves do, if we go on to the next slide, so this is Glen Canyon Dam in Arizona. It's nowhere near us, obviously, but ice shelves act like dams. So they're holding back all of the snow and all the ice and the glaciers that is actually sitting on the land. They're holding all that back. And so if we take a look at the next slide, this is Larsen B Ice Shelf. if the entire ice shelf breaks loose, where we are right now,
All right, David.
yeah. Yeah.
You started to drop off there. Hello.
Okay, can you hear me on this one?
Yeah.
Can you hear me on this one?
Yes, I can.
Okay. So on the Larsen, I think I'm on a different phone.
You're on the Larsen.
No.
Yeah.
I'm on the Larsen phone. Okay. Okay.
You're on the Larsen slide.
No, it's fine. Okay, so the Larsen B Ice Shelf, if it was to completely break away, and it did. Those are actual photos of the Larsen B Ice Shelf breaking apart. And when it broke apart, it wasn't that the sea level rose because of the ice shelf. It was because of what happened next. Because then the dam released all of that snow and ice that it was holding back, and all of that came down into the water, and that then went ahead and built up everything. I think I'm on, yes?
Yes, you are, and you sound much better, actually. It's way clearer.
Okay. I think a whole bunch of things were just happening there. All right, so let's go on to the next slide. And this basically shows where we actually are at. So Antarctica, if you take a look at the peninsula that's over in the upper left-hand corner, that peninsula is what's below South America. And oftentimes when you hear about tourists coming down to Antarctica, they're going down from South America, and they're going around by the peninsula. We're on all the way around on the other side by the Ross Ice Sheet. And we came in from New Zealand because actually New Zealand is closer than anything else to where we're at. So if we go on to the next slide. So this kind of zooms in a little bit more in terms of where we're at. And we are specifically in the McMurdo Shear Zone, which is south of McMurdo Base, which is where we actually made our homes. So the McMurdo Shear Zone, it supports the Ross Ice Shelf. So it's
We lost.
slide.
All right. We lost you for a moment there. Hold on a moment. Are you still there?
Yeah, I'm still here.
Yes, I hear you. Okay. Yes, I hear somebody now. Okay, talk, David.
Sorry, can you can hear me?
Yes, I can hear you.
Great. All right, so I'm going to talk about the McMurdo Shear Zone. And the important thing about the McMurdo Shear Zone is it's providing an important part of friction to the ice shelf. So it's providing friction along the side of the ice shelf. It's a lateral margin. And so essentially it's preventing it from accelerating out into the ocean. It supports the Ross Ice Shelf, and our job is to determine whether or not it's becoming unstable. It's a heavily crevassed region. It's formed by the fact that the ice on the Ross Ice Shelf side is moving very fast, and it shears against the McMurdo Ice Shelf side, which isn't moving very fast. So this heavily crevassed region, we're trying to figure out if it's becoming more heavily crevassed, if it's weakening, and if that translates to less friction applied to the side of the ice shelf. Another important piece of information that you need to know about the shear zone is that the SPOT team, which is the South Pole Overland Traverse Team, they have to cross the shear zone every year, and it's heavily dangerous. So they take all of gear from McMurdo that's really important to the South Pole, which is another base all the way at the South Pole. And so their job is pretty crucial to having the South Pole be operational on that base there. So they have to cross this area that's heavily crevassed. And so we're trying to help them out and determine whether or not this is going to be a feasible place to cross in the future. Great. So we'll move on to the next slide.
Yeah, Lynn, I have a question for you.
Sure.
Mike Penn students want to know how unusual the break-off is.
How unusual.
I think he means the breakup of the Larsen B.
Okay. Of the Larsen B. It was a pretty dramatic event. That Larsen B breakup occurred back in 2002, and it occurred over a matter of a few months. And that ice shelf is about the size of Rhode Island. And so that's a lot of ice that broke off and went into the ocean. It's fairly rare, but it's becoming more and more common. There's another ice shelf right near that one. These are on the Antarctic Peninsula. Larsen C, that we are, the glaciologists as a whole are keeping an eye on because they think it'll break up maybe in the next decade or so. The Ross ice shelf itself is quite large. It probably won't break up in the near future, but we're trying to determine the future of the ice shelf within the next century.
Okay.
Can you still hear me?
Yes, I can. And go ahead, Lynn.
Okay. So, so how do we study this area that's heavily crevassed and an area that we think is crucial for the stability of the ice shelf? Well, so we use a combination of GPS and remote sensing observations. So we're studying how the ice moves at the surface, and we determine something called strain rate. So how, pretty much how the surface is deforming. We also do ground penetrating radar. So we send radar signals into the ice and receive those back, as well as seismic observations. So pretty much energy that's put into the ice shelf, we get returns, and we use that to map the spacing of crevasses and the orientation within the ice shelf.
All right. I think we just lost all of the Antarctica phones. Not sure what happened there. And I saw that there are some people that are posting questions. That's fantastic. Some of these we will get to towards when we have a good break and when Lynn's done chatting, and we get back to David if they're David-oriented or if they are Lynn-oriented. So we're capturing their questions. Don't panic. They just might not happen right away depending on what the question is. Like I started the presentation, the team is communicating by satellite phone, and if you're watching the participant list, they've been the 1-800 numbers are 1-808 and the 888 numbers. Those are the phone numbers that are coming in through Antarctica, and they just all dropped off. And that's not unusual. We were probably pretty lucky that we were able to talk to them for as long as we have. And there they are. Okay. Welcome back.
Okay.
So
I'll just jump right back in.
Yeah. Yes, jump right back in.
Okay. So I think we dropped out, and I was about to talk about numerical modeling.
That's correct.
So we take all of our GPS and GPR observations and observations of what's happening at the side of the ice shelf, and we put that into a sophisticated model that can determine how sensitive the ice shelf is as a whole to changes along the side. So moving on to the next slide. The way we get our GPS observations is we have 29 poles that are drilled into the ice shelf over a 12 by 12 kilometer grid. And we track how these poles move from year to year, and also within over a period of a few hours. So we put a GPS receiver on each of the poles, and it's way more, accurate than, say, the GPS in your phones, and it can actually track how the ice moves over a few hours that we leave it out there. So I don't know if you have the animation that kind of shows those flags moving. Do you have that?
No, we were unable to use the animation, but
okay.
I think
but you have the photo.
Describing what. Yes, we do have the photo.
Yeah, and using those poles and seeing how they move relative to each other. So a lot of poles on one side are moving faster than the other. We can use that information as well. And so the way we actually get these GPS observations, for a majority of the grid that we survey, we travel by snowmobile. We call them skidoo. We travel in safe areas that way, but within the shear zone, the really dangerous area of our grid, it's not safe to travel by skidoo. The only place that's safe to travel across the shear zone is that road that the SPOT team surveys and remediates each year. So how do we do that? We get to travel in a helicopter from a few different sites. And to stay safe when we exit the helicopter, we are attached by rope at all times. So we belay from the helicopter. Sorry, we've got a radio going on in the background.
Driving on the shortcut road from the pier to Pegasus.
Great, all right. So we pretty much belay from the helicopter, so we're attached to it all the time to do that portion of the survey. So moving to the next slide, what we've been able to get from that GPS survey is what's called a velocity contour plot. So this picture is the velocity plot that I solved for using all 29 stations. The warmer colors are on the Ross Ice Shelf side. They're moving a lot faster than the McMurdo side, which are the cooler colors. So on the Ross Ice Shelf side, it's moving around 450 meters. And on the right side of the screen, it's moving 180 on the McMurdo side. And so in the middle, you'll see that there are these lines. These are the contour lines. They are closely spaced. And that means the velocity is changing quite rapidly. And that's that shearing action that's happening in that area. And so essentially where those lines are closest together, that's the most dangerous area. That's the shear zone. So moving on to the next slide. So GPR observations. So we have two different antennas and receivers that we use. So the way GPR works is typically you'll have a person on skis, and they'll be towing a sled behind them with a transmitter and a receiver in it. The transmitter will send waves, radio waves, electromagnetic waves into the ice shelf. Those waves will bounce back off of something in the ice, so some kind of discontinuity. So it'll travel through the ice and say it hits a void, like a crevasse, and it'll bounce back, or it'll travel a different speed through that different medium. It'll travel back to the receiver, and you can use the information about the time that it left and the time that it was received to make inferences of what's going on in the ice, whether or not there's a crevasse, whether or not it's at a different angle to the way you're pulling the sled, that sort of thing. So we have two different frequencies of antennas that we use. So the first is at a frequency of 400 megahertz. All you need to know about that is that it's very high resolution, and since it's a high frequency, the wave doesn't really travel too far into the ice shelf. So this is really good at surveying what's happening at the surface, the crevassing that's happening right at the surface, but it doesn't travel far enough into the ice to give you much information at depth. So we have another lower frequency antenna that can do just that. The 200 megahertz antenna is able to go quite deep into the ice. We've been able to get a return signal from around 180 meters at depth. But using that antenna, we weren't actually able to image the bottom of the ice shelf. From our GPS observations of the elevation of the ice, we know that it's around 270 meters thick. But we're not able to see that far at depth. But we did find something really interesting, was a change in the type of ice.
Don't get too complicated.
Yeah, we're going to go into that in a little bit. But basically we picked up on something called a basal marine ice layer. So we'll go into that in just a second. But you might be wondering, how exactly are we going to ski across the shear zone? Is that safe? Well, that's not. So hopefully you have an image of Linda. Linda was the name of a tractor that fell in to the shear zone in 1990. And this is a large tractor that just fell straight through and was stuck in the ice. It had 2 people in it, but both of them were actually able to get out. The Antarctic, the United States Antarctic program was able to get them out safely, so no one was injured. But that just tells you how dangerous the shear zone can be. So how? Yeah. So how do we go about getting those observations if skiing across the shear zone is dangerous? Because David's going to take over and talk to you about an interesting portion of our survey.
I have some questions. We have a couple of questions before everybody goes away here. So Ann Arts would like to know, how old is the ice on the Ross Ice Shelf? You talked about the depth, but how old is it?
This is Gordon here. We're not dating the ice per se, but it is probably on the order of about 2,000 years since it went afloat. And then, depending on the glacier it came out of, will tell you it's how long it took to come down from the plateau. But it's probably on the order of 7,000 to 8,000 years old.
Okay, great, thank you. A question for David, and actually maybe to relay to the team as well. First, Mike Penn says, we just studied about the Scott expedition and their use of man sleds. My kids are surprised that you physically pull your devices. They hadn't considered how you might do it otherwise. And then there is another question from Ann's students. My students are still confused about what a shear zone actually means. So maybe, David, you could explain it in a different way.
Yeah, so, okay, so a shear zone, think about the fact that a shears is another name for a pair of scissors. So you've got things that are moving in different directions, and that's what causes scissors to actually work. In the shear zone, if you put your hands together so they line up, and you move them together at exactly the same time, then they move together. But in this case, what's happening is that, let's say your left hand is the Ross ice sheet, and your right hand is the McMurdo ice sheet. They're both moving forward, but the Ross ice sheet is moving faster than the McMurdo ice sheet. And as a result, that middle section between your hands gets stretched and twisted, and that's causing crevasses to actually form. And so the zone in between your hands is what the shear zone actually is.
Excellent on-the-fly analogy. Very nice. And before you get into the Yeti, and by the way, we have a link to your movie, but
right.
we'll tell them that, but you can explain what happens in the movie. One student wants to know how, I'm sorry, I'm going back. Oh, Cindy Edwards, third graders want you to know, they want to know how cold it is and how do you stay warm. I know you probably get into some of that, but, third graders, they need that answer now.
They need that answer now. Hi, Cindy. Cindy's in Lake Forest. I used to teach in Lake Forest. Hi, everybody. So how do we stay warm? Well, right now, it's probably about -10, -15, although we are inside a tent, standing up, and it's quite comfortable, actually, at the moment. But when we're outside, we wear lots and lots of layers of clothes. So right now, I'm wearing a pair of wool socks, big boots. I have long underwear on, and then I have a pair of fleece pants on, and then on top of that, I'm wearing a pair of insulated coveralls, and then I have long underwear tops on, and on top of that, I've got another warm layer, and then I've got a fleece on, and then I've got a puffy jacket on, and then I've got my big jacket that I wear that you probably would have seen me wear at school. And then I've got a hat, and I've got a neck gaiter to keep my neck warm. So that's a lot of stuff.
Yes, you're getting a lot of comments about that. We're like, oh my goodness. Yes. So Cindy and her students need to leave, but they wanted to give you a shout out and say goodbye, and thank you for answering that. So I'm going to let you go back to the Yeti, and there's some other questions coming in, but we'll get to them in a moment.
Okay. So Robots Yeti 2.0 and Scotty. So the two-wheeled robots were designed by the Thayer School of Engineering at Dartmouth, which is over in New Hampshire, and the Krell Laboratories. Krell stands for the Cold Regions Research and Engineering Laboratory, also located over in New Hampshire. And they were specifically designed to actually work their way over across the ice. I think that you see a couple of still images, or one still image, of Yeti pulling a sled. So unlike where we would have a person dragging a sled, when we're going across in the shear zone, because it's not safe, we end up using a robot. And not that we don't love Yeti and Scotty, but if they go into a crevasse, it's way easier for them to go into a crevasse and we can extract them than to worry about us. So they tow a sled behind them, and in that sled is the GPR measurements, and they've got a little antenna, which is their GPS measurements, and they crisscross the shear zone, taking data along the way. And then that data we then collect, and then Gordon and Lynn back at University of Maine can go ahead and analyze that data and make some conclusions. So if you go on the, sorry,
yeah,
go ahead.
Just very quickly related to the robots, Anne wants to know, are the robots remote controlled by you?
The robots are semi-autonomous in that they have a series of GPS coordinates, and they know those coordinates. They program them in. Josh and Ben are the two robot guys that are also out here, and they are from the Thayer School of Engineering, and they're in charge of getting all that stuff programmed in. Once the robots get the GPS measurements, then they know exactly where to go, and then they are off and running. So they are semi-autonomous. Can I go on?
Yes, sorry, I muted myself. We are on the GPR view and reality.
Okay, so this is the actual reality of what we're seeing and what actually is underneath the ice. So on that GPR view, you can see that there looks to be like this big thumb almost rising up out of the ice, and that's the void, and that's what we're looking for in the ice. The spot team that Lynn talked about earlier is really important in order to get supplies to the South Pole, and if that crevasse gets too close to the surface, when the spot team goes across it, we could have a Linda-like situation where the spot team goes into the crevasse. And so one of the jobs that the spot team has is to blow up these crevasses, and then they fill them back in. So this individual here in the reality is standing on top of a crevasse that's going to eventually be filled in, but that's the sort of thing that we're seeing out here. So that gives you a little bit of an idea of the scale of the crevasses. All right, so let's go on to the next slide.
That's amazing.
So this is, when Lynn was originally talking about what we were seeing on the ice sheet, the ice that we're standing on right now is coming from the glaciers. But if we go down far enough with our GPR measurements, we're seeing a change in the type of ice that we're looking at. And that ice is what's called basal marine ice. So we have really cold water that's working its way along the ground underneath in the water, and that reaches the grounding line of where the ice is, and it begins to flow up along the underside of the glacier. And as the pressure underneath the glacier decreases, it begins to start to melt onto the underside of the ice shelf. Freeze. And that begins to actually create another layer, which is called basal marine ice. And that should behave in a viscous, deforming way. So think of like silly putty, like you could stretch it, and it's not going to break, it's not going to fracture, it's not going to do anything like we would see in ice. That's what it should do. So if we go on to the next slide, I'm going to hand this part over to Lynn, and Lynn's going to talk about what they actually are seeing.
All right. Yeah, so when we picked up on that new layer of ice within the ice shelf, we actually weren't sure what its properties would be like. The ice is different than, say, sea ice that freezes. It's frozen seawater at the surface, because it's formed from a mixture of fresh water from the glacier, outflow of the water coming out from underneath the glacier, and it mixes with the salty water underneath, so it's slightly salty water. But what we've noticed is that it's crevassed. We've picked up on crevasses within this layer as well. But these crevasses are in the same place as the surface. So the next, if you'll go to the next slide. Yeah, so this actually opened up many, many different or new questions as to what this ice, how this ice behaves, and why it's crevassed in the way that it is. When we think of basal marine ice and crevasses on the underside of the ice shelf, we actually think that they form all the way up where the ice comes afloat. As the ice comes afloat from off the bottom of the seabed, it undergoes these buoyant forces, so it flexes and creates these pretty large crevasses. But what we're seeing is that the basal crevasses that we see in our GPR data is that they are crevassed in the exact same region as the ones that we're picking up in the surface. And so we think that they're formed from shearing as well. That's really the only logical explanation that we can come up with now. So that's giving us a lot to think about, sort of why this ice is breaking in a similar way to the surface, and what are the properties of that ice layer. So moving to the next slide. This is showing something that the two, so last year's GPR survey was done in the green box. So this is around the shear zone. It's near our base. This year we decided to move further south to the purple box. Again, that your orientation is flipped. But we're trying to get closer to the rifts that are happening around Mina Bluff. We're trying to determine whether or not these crevasses have anything to do with the rifting further upstream. So if we'll go to the next slide, in order to answer some of these questions about the properties of this ice, we're trying something new this season called seismics. This is a picture of a sled that's got a decent amount of dynamite on it. And this is pretty typical of what the SPOT team actually brings out when they remediate those crevasses and set off those explosions. So if we'll move on to the next slide. This year we're going to set up a seismic array. So in red is the road that crosses the shear zone. And the green stars is the array of what we call geophones, what we're going to stick into the ice to pick up on that energy that is released from those explosions. And so going to the next one, spot blasts, essentially if you trace from 2 points along the road where they're going to set off those explosions, and you trace lines out to all of your seismic arrays, these are all the waves that we can pick up on. And we can use that information to figure out what's going on at depth. And if we move on to the next one, we actually will be able to get some information from the SPOT team as they cross the shear zone. So not only are we going to pick up on the energy that's released into the ice shelf from the explosions, but when they have a decent amount of tractors that cross the shear zone and travel along the road, we can trace the rumblings from those tractors across both sides of the shear zone. So as they're crossing and as they're coming back, we can use that information. So what we hope to get from the seismic array is, since it's a lower frequency, we will be able to go all the way to the bottom of the ice shelf and probably even further into the ice column, maybe even to the seabed floor. So we're hoping to understand some of the properties of the ice, that basal marine ice layer, how stiff it is, and we think we can get that information from the seismic array. And so finally, moving on to the next slide, is some pictures of the numerical model that I've been working with. So the end goal is that I will take all of the information from our field observations, some from satellite remote sensing, and feed that information into a sophisticated model that can solve for how the Ross Ice Shelf will change with time. And so the first thing that I have to do with the model is calibrate it. So the right portion is the observed velocity of the Ross Ice Shelf. The warmer colors are moving faster. The colder colors are moving slower. And again, we're in the corner of this ice shelf. And on the left is the model velocity. So this is what I've been able to get the model to solve for based on current observations. So I believe that this is doing a pretty decent job. I'm hoping to improve it a little bit more. But once it's calibrated, I can test it, and so I can make changes in the shear zone and see how that will affect how the ice changes with time. And I can specifically try to solve for how the glaciers speed up, that feed into the ice shelf when that ice shelf is not applying as much stress. So again, that sort of dam analogy. If it's not pushing back on those glaciers as much, how will those glaciers speed up and contribute to sea level rise? So in summary, we're completing our last of 3 field seasons. We've acquired a robust GPR data set where we've picked up on surface and basal crevasses in the same location, and they match with our GPS strain rate grid, so where that shearing is occurring. And this year we're hoping to see how properties of the shear zone are inherited from Mina Bluff, so the rifting from upstream. That's why we moved our survey grid. And this year we're also doing a seismic grid to understand the ice at depth. And finally, I'll be putting all of that information into a numerical model. So go to the next slide. Do they have it?
Don't have the video, but yeah, talk about it.
Okay, so I just wanted to do a quick plug for another outreach opportunity that I've been doing this year called the Follow a Researcher program. It's through the University of Maine, the cooperative extension that we have there. And essentially, I've been putting out weekly videos. These are the videos that I put together before I came out into the field. They're online, and they take students through the scientific process. So from the beginning, where we're asking questions, where we want to determine what we're studying, to acquiring data, to and putting all that together through modeling and understanding what we were able to get. And so you can follow me online, and we actually do weekly Twitter sessions as well. So you can send in questions that you might have, and we will answer you from the field. And, yep, Gabe will wrap it up.
Okay, so the last slide shows the big warning signs on either side of the crevasse zone, and we're literally camped about 50 meters away from that sign. I know we don't have very much time, but myself and Lynn and Gordon are here to answer any questions that you have.
All right. Yeah, we can take as much time as you all need, and we're just astounded that you have been able to be on a satellite phone call for over 20 minutes now, at least.
It's pretty amazing.
It is. I probably just jinxed us all. But anyway, I'm going to back up to some questions that came through the chat while we did that, and I just also want to let Lynn and Gordon know that somebody from a University of Maine Follow a Researcher is actually with us on this event, and they're posting the links and everything as well. So, and we appreciated the shout out. So from Broadwater Academy, Sandy Thornton wants to, and her students want to know, what has been the biggest challenge you've found working in Antarctica? And that probably goes to any of you.
Gordon, you want to talk?
The obvious, this is Gordon. This is my 19th season down here in Antarctica, and the biggest challenge is the same every year, and it's the cold. Seems pretty obvious, but kind of cold rules everything down here. Batteries and equipment drains faster. People work slower. We have to spend a good portion of our working day just actually trying to survive. So we have to make ourselves warm, build safe shelters. We have to melt all our water. And it seems like a large portion of our day is just dealing with the cold. So instead of working a 9-to-5 job that we would do back at home, we probably spend only 4 or 5 hours actually doing scientific measurements every day, and the other part of our workday is just trying to deal with the cold. So it's a major challenge. So it's kind of surprising that the Antarctic program is so successful, but people are very resilient and determined to work through these cold conditions. But certainly, cold is a real challenge.
Okay. I think that also relates, Mike Penn earlier, and I think this relates to what David was talking about, being the marshmallow man and all of his clothes. He mentioned a temperature, -10, -15, and we were wondering if that's Fahrenheit or Celsius.
That particular temperature is Fahrenheit, and the important thing too, though, to remember is that it drops even lower with the wind. We get some pretty major katabatic winds that are blowing down the Ross ice sheet and across the McMurdo ice sheet, and those drop the temperature down even farther. Not to mention when we get onto snowmobiles and we start actually driving the snowmobiles going, 20 miles an hour across the ice sheet, that further increases the temperature drop. So it gets very cold very quickly.
Okay. From Lawrence Central School, they want to know, how much fuel do you use in a season to heat? So maybe at the tents, how much fuel did you bring out to your area?
Okay, so we're here for, this is Gordon again, we're here for 3 weeks, and we're about 50 miles from McMurdo Station, so we had to plan very carefully how much fuel we brought with us. And to heat the tents and to for fuel for our stoves, we use propane. It comes in tanks. It's the same kind of propane tank that you probably have on your back porch for your cookouts. And we brought 20 of these canisters of propane. And whether we use them all or whether that's enough, that's something we have to estimate before we leave town. But hopefully that should be enough to last 3 weeks.
Okay. And our students want to know, how many hours of daylight do you have right now?
At the moment, we've got basically 24 hours of daylight. The sun doesn't actually set.
It'll go behind the mountains.
It goes behind the mountains, yeah, but it doesn't actually set. It never goes below the real horizon.
Okay. I can tell you I live in Alaska, and we're down to 9 hours in Anchorage, and probably less further north. I'm jealous. Let's see. Going back to that cavity that you had the picture of the spotters and blowing up the cavities, so that's kind of where we're going with the next suite of questions. Lauren Central School wants to know, how do you fill them in? I explained that you blow them up, but maybe you can go into a little more detail.
The spot crews, when they come through, they have quite a bit of machinery out here. And just like if you were at a ski resort, they take a snow plow, and there's no shortage of snow, and they push that snow into the crevasse, and they fill it in enough so that they can drive it over.
Okay. And the next one, when we were looking at that picture of the cavity, Mike Penn was wondering, does that cavity extend all of the 250 to 300 meters down to the water, or is it must be shallower, I guess?
No, that is definitely doesn't go all the way to the bottom. But for a scale that's about 6 meters wide, and it starts at about 6 meters depth, and it definitely closes off by around 25 meters depth, but I don't know the exact number.
Okay. Ann Arts would like to know, is there a significant difference in the salinity of the basal marine ice layer?
Yes, definitely. So it's, I don't know the exact salinity. It's slightly salty, again, because it forms from a mixture of fresh water and seawater, whereas, say, the sea ice that freezes out in front of the ice shelf, frozen seawater, that's very salty. And then the ice that's the glacial ice, that's all doesn't have any salt. It's fresh. So hopefully that'll give you that concept of the different quantities.
All right. Very quickly, and then I have a couple more questions, but Sid Kyle wants to say hello, David, from sunny and warm Los Angeles. And,
Hi, Sid.
and Mike Penn and his students have to go. They say thank you very much. We appreciate this. We are signing off. It's 3 p.m. here in Pittsburgh, and we are dismissing. So thank you.
Thank you so much, Mike.
Yeah. Okay, back to a couple more questions, and that will probably be it. But Anne would like to know, is there a way to access the results of your work, and when and where will it be published?
That's a great question. So as scientists, we're funded by you, the taxpayers, and so we have an obligation to make all of our research public. So like with any scientific project, there's several years of data collection and analysis, and we're in that phase right now. But beginning in maybe the next 6 months, we will start writing up our interpretations of the data we collected. And that is published in, or is presented in several different venues. One, we can go to scientific conferences and talk to our colleagues about what we've discovered. Then Lynn, who's on the phone here, is going to write a nice, thick PhD thesis, which will describe all of the results and give a full background to all the methods we've used. And then the investigators who are part of this project will write papers that are published in scientific journals. And because we're publicly funded, these papers have to be open and available to anyone to read. But with any scientific project, it takes several years from conceiving the idea, collecting the data, submitting the results for publication, and then actually seeing the results in printed form. It's a 3 to 5 year process.
Yeah, a lot of work ahead. So I want to let you guys know that Maggie Keynes, RMSEL Senior, say thank you, David and team. So interesting.
Thank you, Maggie. Have a great trip yourself.
Yeah, she's headed to Chile to join the NASA Operation Icebridge team here in a matter of days. So we look forward to hearing her adventure as well. Yeah. From another fellow alumni from CARA, we have, are there other research groups that are doing similar studies on other areas of the Ross Shelf or other ice shelves in Antarctica?
We are the only group on the Ross Ice Shelf right now. There are groups working over on the Antarctic Peninsula, which is the thumb of land that sticks up towards South America. And I think Lynn mentioned earlier some smaller ice shelves there, the Larsen Ice Shelf, Bellingshausen Ice Shelf. So there are some groups working there. These ice shelves are much smaller than the Ross Ice Shelf that we're studying. It makes them a little bit easier to study them. But hopefully the results that they find on these small ice shelves are also applicable to the large Ross Ice Shelf that we're studying now.
Okay. Let's see. Sorry, I was doing something here, but I think that's it for our questions. And well, people are getting ready to go back to their classes and do other things today. Before you sign off, please fill out our polls that are online and give us a feedback about this event. And in the meantime, I just also wanted to relate to everybody that's joined us virtually that we have another PolarConnect event coming up from from Maggie when she gets down there to Chile. It's in a couple of weeks in early November, and we have other teachers that are in the field also in Antarctica that will be doing events through November and December. So please stay connected with us through PolarTREC. And this event itself will be archived, so if you had to sign off or you have other people that wanted to see this event, it'll be archived, and we'll share that online and send it out to everybody that registered. And yeah, we had a great connection with you guys, and I really want to thank the team for joining us today. It was really fun to hear about your science, and it sounds like you've been busy and hopefully not too cold and eating too much more frozen pizza.
Well, thank you very much. The frozen pizza is delicious, but it's almost all gone. But it's time for breakfast here and some more coffee.
I hear you on that. I think we're good. So I'm going to stop the recording, and if there's friends or family that want to give a shout-out, you're more than welcome to turn on your mics and do that while I kind of wrap down our end of the event, and thank you very much.
Thank you.